All right, so this is the first one with the practice test. You want me to talk about this one, or you want me to talk about the other one? The other one? You just do whatever you like there. But I want to be the one to manipulate it. So I was not the... All right. All of it? Okay. No problem. 300-kilogram box rests on a platform attached to a forklift as shown above. Starting from rest at time equals 0, the box is lowered with a downward acceleration of 1.5 meters per second squared. Determine the upward force exerted by the horizontal platform on the box as it is lowered. I hope you recognize this as the elevator problem. That's really what it is. There are two forces acting on the box. There is a downward force of weight, mg, and an upward force of normal, and they are not balanced because the system is accelerating downwards. So net force equals ma, and I'm not going to deal with x or y direction. This is a one-dimensional problem right now. So let's go with normal minus mg equals m times negative 1.5. So we know that the mass is 300. So this is normal equals 3,000 minus 300 times 1.5 is what, 450? So 2550. It's nice, it has numbers. At time equals 0, the forklift also begins to move forward with an acceleration of 2 meters per second squared while lowering the box as described. The box does not slip or tip over. Determine the frictional force on the box. Okay, so now it's accelerating this way too. So I guess I can add that there has to be a force on the box in this direction. And that's the only horizontal force acting on the box. It is friction that accelerates the box. I'll point out they are careful to make sure in the picture that you see that there is not a normal force on the box that is horizontal. So it's only friction accelerating this particular box. Net force in the x direction equals ma. Friction x in the x direction, and that's 300 times 2 for 600 newtons of horizontal frictional force. Yep. Well, if we don't want the box to slip, remember the box wants to stay in place. We're trying to make the box go to the right. So if there was no friction here, then the forks would just slip out underneath it. So in order for the box to go to the right, and in order for one surface not to slip past the other, there had to be a frictional force that acted on the box at the surface in this direction as the pushing force to act on the box. Does that make sense? Otherwise, there's nothing in the forward directions to cause the box to go that way. That was pretty easy. C, given that the box does not slip, determine the minimum possible coefficient of friction between the box and the platform. This has to be static friction because there's no slipping of the box. There's really very little to do here. It is an inequality already. We're going to sub into the inequality. So 600 has to be less than or equal to mu times 2550. That's it. So mu s I don't know what that is, but it's clearly less than 1. And that's a greater than, equal to this value. So this represents the minimum. It can be greater than this. It just can't be less than this number. D, determine an equation for the path of the box that expresses y as a function of x and not of t, assuming that at time t equals 0, the box has a horizontal position of x equals 0 and vertically y equals 2. All right. Again, I will point out these right in our wheelhouse, right? Beginning of the problem. You get this far, probably getting a 3 on the exam. Now we're going to see if you can be a thinker. That should get you to your 4. And if you can do it without any mistakes, probably a 5. So I think this question throws a lot of students off because they're talking about, you can't put t in there. Well, that's probably true, but for right now, I think we're going to have to just put t in there. Let's look at the x direction. In the x direction, delta x is x minus 0 because the initial position is 0. The initial velocity is 0, and the acceleration is 2 meters per second squared. Well, I can combine all of these things and put it into a motion equation. X minus 0 equals 1/2 a t squared. You see, what I'm going to do here is the same thing I've done for projectile motion, which has always been to find the time in one and sub it into the other. If I find another relationship for y as a function of t, then I can eliminate t between those two relationships. Meaning delta y has to be y minus 2 because it starts 2 meters above the ground. The initial y velocity is 0. The acceleration is downwards at 1.5 meters per second squared. That means y minus 2 equals 1/2 times negative 1.5 t squared. Take a look at this one. That's x equals t squared. Take a look at this one. That's y equals negative 0.75 t squared plus 2. We want y as a function of x. Substitute. X equals t squared. So y equals negative 0.75 x plus 2. Y is a function of x. Yeah, probably not a lot of you thought to do that. That's why it's on the practice test. Now, again, I think this gets you from a 3 to a 4. And I think the next part gets you from a 4 to a 5. So on the axis below, sketch the path taken by the box. The box starts at 2 meters. Right? That is the y-intercept of this function. This is y as a function of x. This is a straight line, by the way, with a slope of negative 0.75. Now, the problem with that is the slope is negative 3/4. So I would go down 3 and over 4, except that this is 1, this is 1, this is 2, and this is 3. So my scale on the bottom isn't the same as my scale on the side. I think that's on purpose to just screw with you. So instead of going down 3 and over 4, I'm going to go down 1.5 and over 2 because my brain works that way. So go down 1.5 over 2. And this line should be lined up with this function. Now, I should not stop there. I should redo this and extend the line all the way until it touches the x-axis, but not below the x-axis. The box can't go below the x-axis. So it has to stop there. You want to get a 5? Yeah, that's what you're going to have to do. Level of difficulty, I'd say the beginning of the problem wasn't particularly difficult. But I think that the end of the problem, I think it threw a lot of people off. Of course, there are people who just, their brains wrap around this nice and quick. That's good stuff. Way to go, smart brains. All right. That was the 2 FRQs, and it did not take us 30 minutes to do them. So clearly they can be done in less than 15 minutes each, if you're Mr. Shelton. Although I needed to be corrected, so who knows. Would anybody like to talk about anything else from the homework, since we've covered all the FRQs? Yes, sir. I don't know. What is number 39 on chapter number on that one? Okay. This one? Yes. All right. So where would you like me to begin? At the start of the problem? These two problems are straight off the actual AP exam. They are directly from College Board. Both of these problems were given in the 80s and 90s. They're well within our, in fact, if these were on the exam, thank yourself. This is a good one. These are solid performers. They're not particularly challenging. And although you might not have been able to be successful on it, by the end of the year, I expect that these would be actually at the lower end of the difficulty level. We've not been using authentic FRQs on our test yet. We've been using either parts of actual FRQs or drastically augmented problems, but this is the kind of problem that is a single topic question for the AP exam. It's hard to find those, but this was given a couple years ago. Obviously, they want a free body diagram. They give you more space than this on the actual test, so don't think that that's the only space you have to work with. You have lots of space to work with. This has been compressed to fit in a smaller page size. So if we want to start at the very beginning, free body diagram, I would be careful about how you draw the length of these arrows. If we start with the weight, that one's pretty straightforward. But this force off to the side, kind of be careful in how you decide to do these. This one, F1, pulls upwards about that much. I'd say that's maybe slightly less than half of the weight. So my normal force should be a little bit bigger than that. Set together, the upward force from the normal force and the upward portion of F1 equal out with mg. And then using what I just kind of put together for F1 and normal, recognize that this represents the size of the frictional force. And it looks like it's almost the same size as the normal force. Trying to make sure we understand that friction is likely to be less than, but at max equal to the normal force. So I think something like that would be okay as your free body diagram goes. Question B, derive an expression for the normal force exerted by the surface on the block. Well, this is just drawing the free body diagram. Yes. Okay. I did not read close enough, apparently. Oh, you're right. This is the one that has A1 as our acceleration. So there we go. Much better. So now we know it accelerates this way at A1. So, better. On your test tomorrow, you will have probably an area where you will have to draw a free body diagram that you will not be able to work on, meaning just a free body diagram. If that's there, I mean, I know I've done that for one version of the test. I'm still writing the second version of the test, so I assume there'll be something similar on the second version of the test. So my expectation for you guys is prepare to draw a free body diagram and then separately have something where you put the coordinate system down and all that. So coordinate system, I think this one's pretty easy, straightforward, right there. It's accelerating horizontally, so I want this to be horizontal. This is theta, and we've got F1 cosine theta here, and F1 sine theta there. Acceleration is not a force and doesn't really have a place on the force diagram, but it's appropriate to know what direction the acceleration is. Once I have that, it says derive an expression for the normal force. So net force in the y direction is equal to 0. I see 1, 2, 3 forces in the y direction. So normal plus F1 sine theta minus mg equals 0. So normal equals mg minus f1 sine theta. You're allowed to have all of those in your answer, so that's just fine. Deriving expression for the coefficient of kinetic friction between the block and the surface. So this one, a little more. Net force in the x direction equals ma. It is accelerating, as stated in the problem. There appear to be two forces in the x direction, F1 cosine theta and friction. And the only reason I'm doing this is because I know that to get the coefficient of friction, I will need the frictional force and the normal force. So I'm kind of skipping the part where I realize that this is true and just continuing solving a Newton's law problem to see if it's going to give me what I want. The fact that I got the normal force last time kind of hinted me that I'm probably going to need to get the frictional force this time. There's F1 cosine theta, and there's friction, and they have to equal ma1. So the frictional force is ma1 minus F1 cosine theta. Skipping some algebra steps, but I think I'm okay to do that. We okay so far? So to get my answer, just put ma1 minus f1 cos theta in the numerator and mg minus f1 sine theta in the denominator. Seems good to me. All right. On the axes below, sketch the graphs of the speed and displacement of the blocks as functions of time. The block started from rest at x equals 0 and t equals 0. There's an important word here. It doesn't seem that important, but sketch instead of plot. Sketch has the lowest threshold for what needs to be presented, which is good. We don't have much information here to present. We know that the acceleration is constant, so v as a function of t just has to show that it is a constant. Yes, sir? Yep. It would. It took that long for somebody to find my mistake. You guys aren't really paying attention. But I appreciate the correction. This should have been f1 cosine theta minus ma1. I was doing my algebra too fast in my head. Probably from having done this problem 3 times today. I think I'm just doing it in my sleep, but apparently not. So now I got to correct my answer here. Oh, don't sigh so exasperated. Like, if I can make a mistake in front of all of you, you can put up with it. Okay, getting back to where I was. The acceleration is a constant. So my velocity has to be a constant. That's all you have to do there. And if you recognize that the acceleration is a constant, then you realize that the position function has to be the square of the time. So basically all we're saying is that v equals at plus v naught here, and x equals 1/2 at squared plus v naught t here. We're just using a motion equation. If the acceleration is constant, both of these apply. So as long as you have it concave up, you should be fine. Yep. It would be slowing down. It's concave down, and our object's speeding up. We should have the slope. The slope should be increasing because it's getting faster and faster. And more importantly, these two should be in agreement. So I'd say that most of those were relatively pedestrian, but question E's where it really asked something interesting. Yeah. We good? Okay. So question E asks for something specific. It says, if the applied force is large enough, the block will lose contact with the surface. Derive an expression for the magnitude of the greatest acceleration that the block can have and still maintain contact with the ground. Poorly worded question, actually. And I'll explain why in a minute. If we consider what we know about this problem, and that is that the that F1 cosine theta minus friction equals MA1, and that the normal force equals mg minus F1 sine theta. If we consider those two things are things that we know. They're saying that the applied force is large enough that the block will lose contact with the surface. That means that the normal force approaches zero. That's the condition where we're losing contact with the surface. The surface can't apply a force if it's not in contact. So as we pull harder, we are pulling with an upward force that's greater and greater and greater. The normal force doesn't have to be there anymore. Now, what's also true is the frictional force then also must go to zero. Friction is proportional to normal. So if the normal is going to zero, the frictional force is going to zero, which means F1 cosine theta is going to be equal to MA1 at the moment the normal force is no longer providing a force against the object. The surface is no longer providing a force against the object. And F1 sine theta equals mg. Here's the problem. They let us use all of the letters in our answer. So on the answer guidance for this year, people, being shrewd and realizing that they're allowed to have all of these in their answers, gave this for their answer, and it had to be accepted even though this is not what they wanted. I mean, this has to be approved. It has everything in it that is allowed in the answer. That's not actually what they were going for. They were saying that F1 was great enough for it to lose contact, and they wanted the acceleration, or the max acceleration that would make that happen. And although this is all true, they would like you to consider that the max acceleration is something about the angle and less about that applied force once you are pulling hard enough for it to lose contact. So what they really wanted you to do is find a way to find A max in terms of as few as variables as possible. They didn't make that clear, though, so they had to accept both answers. Now, to find it in terms of the fewest variables as possible, I would consider that I have an F1 sine theta and an F1 cosine theta. When I see those, I'm trying to encourage you to put them together. And then divide them. Because when you do that, you're bound to get rid of something. And in this case, we get rid of the F1s and the M's, making this not about the applied force and the mass, but something that will tell us what the acceleration is. So we've created the condition where F1 was great enough to deal with the mass. What does that give us for A max? So, by the way, sine over cosine tangent. So tan theta equals G over A max. So A max equals G cotangent theta. Just cross multiply. I mean, you could write this as G divided by tangent theta too, that's fine. This is more interesting and provides a more interesting answer. And this is what they actually wanted you to do on the exam. It's unfortunate because they didn't stipulate that. Nowadays, they would be far more stipulating. They would indicate what you could use in your answer, or they would phrase this a little bit differently. All right. That is the whole thing. I would say that if you look at the nature of this question, and I'm probably looking at it from a different standpoint than you are, but look at the nature of this question. They ask several parts in the beginning that are right in line with the kind of stuff we've done. And it's not uncommon for them to do, starting off with things that they think are familiar. And then they start, it looks like somebody changed what I did there. Stop zooming in, whomever you are. This is my paper. Won't let you have contact anymore. Keep zooming in on your own. So those aren't the things I wanted to highlight. These are. D took it to a different place a little bit by having a graph, but come on, had you graph what a uniform accelerated object looked like? It's not really much either. And then there's a part here that takes it a little bit another step. Can you deal with, what happens under a situation where they're asking for you to try something? If you look at the way the point distribution was, I believe this was worth 4 points on the actual AP exam out of 15, which means 11 points out of the 15 were purely based on stuff that you could almost, I'd hope, follow a procedure and get towards an answer. And that's why this is worth a 4 on the exam. But if you want a 5 on the exam, you got to get a couple of these points. Now, if you want a 3 on the exam, well, forget how to do some of this, like blow the graphs. People will blow the graphs because they're not thinking. They can follow a procedure, but can't extend to change what the problem is about. Then you're probably looking at a 3 on the exam. Unable to follow a procedure, 2 on the exam. Don't know what Newton's laws are about? Well, that's as good as a 0 on the exam. All right. Next. Yes, sir. The other one. So it looks like I have some beam, and there are 2 ropes holding this up. One like that. One like that. And there. We're told that this is 20 degrees and this is 30 degrees. All right. I'll do most of this problem. I think once we get to the tedious algebra, I'll probably stop. But let's see if we can't, set this problem up. Free body diagram, probably the best way to go. There's something about this free body diagram that I would be more than willing to be testing tomorrow. So, weight downwards. Purposely drawing that nice and straight and relatively large because I have 2 forces acting upwards. Now, regardless of which one of these you draw first, be careful. If I draw the 30 first, I'm paying particular attention to how far to the side it goes. The net force has to be 0, and the 20 has to be drawn at a shallower angle, so it will have to be drawn longer in order for its sideways portion to be about the same as a 30-degree sideways portion. So I think I've drawn both of them too long, to be quite frank. Because I also have to recognize that this portion plus this portion has to be equal to the entire weight. So the big takeaway here that I think should make it into your notes is that the tension on the left side, which I'm going to call T1, has to be greater than the tension on the right side, which I'm going to call T2. The one that is more straight up and down is going to hold more of the weight than the one that's at an angle. It's always going to be true. I gain no special advantage lining this up with either of the tensions. So I'm going to line it up with the weight. Which is a little disappointing because that means I have to break up both of these into their components, but that's what I've got. So something like that for the one on the right. And something like this for the one on the left. It's kind of hard for me to write in there. But can we see that this and this are going to be based on the sine of the angle because they're the opposite sides? And both of those will be based on the cosine of the angle because they're the adjacent sides. So when I start looking at my net force in the x direction, which has to be 0, I will have T1 sine 20 equals T2 sine 30. The part I pull to the left is equal to the part I pull to the right. And T1 cosine 20 plus T2 cosine 30 has to equal mg. There's no special way out of this. You need to solve one of these for T1 and plug it into the other. I think the best way probably is just to do T1 equals T2 times sine 20 over sine 30. You're not going to gain anything special after that. I mean, nothing's going to cancel out in a nice, neat little way. You can get a cotangent in there, but who cares? Just take sine 20 and divide by sine 30 and get a decimal. Plug them in there. The only thing I will say is that sine 20 divided by sine 30 kind of tells you the ratio of T1 to T2. And I think I've gotten the ratio wrong, and nobody corrected me, so I will correct my own mistake. Should be 30 on the top and 20 on the bottom. Notice that this is greater than 1. I noticed it. You should notice it. Has to be. T1 is greater than T2. So that proves it. But either way, that's it. I don't want to keep going because after this, it just becomes mean math. But you're going to get some decimals in there. Factor it out. Divide by mg. Enjoy your fun times. All right. Another homework question? $47. Yep. I worked with another student on this too, and I can see why there's an issue with this problem. I think this is a bit of a ridiculous question, and I'll explain why in a minute. But basically, it's not particularly realistic. All right, so the truck's going up the ramp. It's traveling at a constant velocity first. So with that being said, we can put together that there is a weight of the truck. There is a, I don't know, the force from the truck, its engine, acting on the truck to push it up the ramp. There's got to be something that does that. And then there's normal force. We are told to ignore friction. They say we're told to ignore rolling friction. And that's, I think, a distracting thing to say. They really mean for you to ignore friction, which is stupid because the truck can't apply a force to the surface without using friction. It uses static friction. But they would have been better served if they just made this a box being pulled up by a string than trying to make it a truck problem. Because what they want you to do, and part of the reason I assigned it was for this purpose, they want you to use the fact that when the load falls out of the truck, that the force from the engine doesn't change, but suddenly the mass of the system does. And if the force from the engine doesn't change and the mass of the system does, then the frictional force is reduced. There's no friction. But the component of the weight down the ramp is also reduced. and that matters. So what I mean is net force in the x direction equals 0 before the load falls out. So the force on the truck from the engine minus mg sine theta equals 0. Any question about that? So this is the force from the engine, which is 7,500 times 10 times the sine of 15 degrees. Suddenly, the load falls out of the truck. So suddenly, the net force on the truck has changed and the truck begins to accelerate. We don't know what this mass of the truck is. It just lost the load. We do know that the engine from the truck hasn't changed, but the mass suddenly has. Since we know what the force from the truck is, we could use that to figure out what the new mass of the truck is. Now, that's not the answer to this problem. This is the new mass of the truck. 7,500 was the old mass of the truck. If you want the mass of the load, you'll have to find the difference in the mass of the truck and the new mass of the truck. So I can keep going if you need a numerical answer, or is that enough to figure out what you have to do next? Okay. It's not a particularly great problem, but I think it's something for you guys to do a little bit more incline work on. Well, bell rings in 1 minute. Tomorrow, 2 FRQs, 10 multiple choice questions.